Hi everyone, I am Agniapta Sinha and with me is Pratay Banerjee and welcome to our presentation on from external correction to internal alignment, embedding reliable reasoning in large language models. The motivation or the goal of our project is in two parts. The first part is to check uh, which layers we need to fine tune in an LLM to get the best results for a given task, which we compare the performance of middle layers along with earlier layers and later layers of an LLM. We do the fine tuning with CPO, and we ask it to, and we have a task, a predetermined task, and we check the performance of each of the processes. And the second part of our motivation or the goal is steerability, which is we use sparse autoencoders or SAEs to replicate the fine-tuning process during inference time in real time of an LLM. So if a CPO model has fine-tuned say XYZ layer, we try to replicate that with SAE and see how much of the fine-tuning process SAEs can imitate. The problem statement and hypothesis for the layer specific CPO, we applied a CPO to five sets of layers. Middle layers were the the total number of layers were 28, and the middle layers we applied it to 10 to 16, then 14 to 20, and 18 to 24. The earlier layers were 1 to 7, and the late layers were 22 to 28. We find that layers 14 to 24 give the best accuracy out of all, which proved our hypothesis that in fact middle layers do the heavy lifting of the logical reasoning steps or the chain of thought steps in an LLM. We used essays afterwards to check which specific activations were getting activated in the 24th layer using an SAE. We checked that essentially we discovered that CPO acts as a semantic pruner, which we mean that it reduced most of the activations and increased some of them, which meant that CPO was effectively removing noise from the LLM, which allowed it to generate better reasoning or COD steps. And for the proof of concept, like I said before, we use the same SAE that we trained for hybrid feature steering, uh, which we try to replicate the fine-tuning process with SAEs, and we discovered that we can recover 73% of errors on a data set with the base model, which was an unprecedented finding that we got from this project. The experimental setup for the base model, we used Qwen 2.57b. There were 28 layers and the hidden size was 3584. For the dataset, we used GSM 8K, both train and test. For environment, we used a Colab A100 and L4 GPUs, 4-bit quantization, and PFT with LoRa. And the latent dimension size of the SAE was basically 3584 into 8, which is 28,672. How we created the triplet data for CPO. CPO requires prompt chosen and rejected. We generated the LLM response firstly with the base model for the entire GSM 8K train. We then used regex and more complicated formatting to see which answers the LLM gave right versus wrong. We discarded the right answers, we took the wrong answers. That was our rejected. The chosen we got directly from the GSM 8K data set. There's a answer column. We just took that. And prompt was, of course, the question. The data set was approximately 5,000 rows. You can see on the screen, this is the loss. This is the the loss during training for the layer specific CPUs. If you can see that the green one, which is 10 to 16, had the least loss, but surprisingly, it did not fare well in our test data set. But layers 18 to 24, the orange line, it is pretty high up, but technically that was the best model we got. Yeah. This is the test accuracy of the models compared to the base. The base is on the left-hand side. As we can see, most of these had an improvement over the base, except layers 10 to 16. Uh, we find that layers 18 to 24 had the most increase, and for the next steps so throughout the project, we use this model for like SAE training and analysis and all that. But the main thing is, even though this is not a substantial increase in accuracy, we find in the data set that all of the CPU models generated was the structure of the answer had significantly improved from what the base model gave a lot of verbose answers. The CPU model, especially the 18 to 24, generated answers that were closer to the GSM 8K. If you're familiar with the GSM 8K, you will know the answers are very short and to the point, which is a good thing. But unfortunately, math were like doing math, we could not increase drastically. We increase some, but not drastically with CPU. This is a comparison of both train accuracy and test accuracy that we generated with base and all the CPU models. Although 18 to 24 was not the highest on train accuracy, it was the highest on test accuracy, and we went forward with it. Yeah.
So after the CPO training out, the phase two of the project involved using a sparse autoencoder. So sparse autoencoder is basically an autoencoder with a encoder decoder architecture, but it what it does other like differently than an autoencoder is it like enforces sparsity. Like when it projects the input to a latent space, it projects it into a much higher dimension, which helps to better disentangle dense activations of neural networks. And like it's much easier to understand a dense activations of neural networks because the like the activations are projected into a much higher dimension and they can be divided into individual features, and it can be much easier to understand that like activating which feature or like steering which feature is causing a certain effect or a result. So SAEs are primarily used to that for that, like to disentangle dense activations. And the architecture that we used was a similar one. Like we used encoder followed by a ReLU activation and then a linear decoder. And the dimensions that we chose were like the model dimensions multiplied by 8. So 3584 multiplied by 8. So we projected into a much higher dimension of the input activations. And the loss, how we calculated was the reconstruction loss plus lambda into sparsity loss. Lambda is basically, lambda is basically the sparsity factor, which penalizes which basically controls how sparse the activation will be. So a higher lambda will make your like the will make the projections of the input much more sparse, while a lower lambda will make it less sparse. And we like experimented between multiple lambdas, and the best lambda chosen was 3 to the power minus 3 because that had the best balance between reconstruction loss and sparsity loss. And after that, here, if you see like the comparison, so what we did was like we had to train this SAE, right? So we took the activations from the 23rd layer, like as Agni mentioned, like between the 18 to 24th layers, that model performed the best with CPO. So what we did was we took the activations from the, like using a hook, we took the activations from the 23rd layer, and then we trained our sparse autoencoder on those activations, both from the base model and the CPO model, so that we could compare them and disentangle the features and have a much better understanding of those activations. And what we see, like we then compared using the L0 norm and L1 norm to better understand the sparsity of those activations in the latent space. And what we saw was that the L0 norm was much lesser, and the L1 norm, both the L0 and L1 norm were much lesser in the CPO model. And that makes a lot of sense as well, because L0 norm is basically the count of features, the number of active features. So if it's less, that means far less features are active in the CPO model. That means it's much more, it's activating much number of lesser features, and it is suppressing the erroneous features. So that makes a lot of sense, because the CPO model's accuracy is much higher than the base model. So it's guiding the model towards the correct answers with much less number of activations. And L1 norm is basically the magnitude, the absolute value of those activations. So which is also much lesser for the CPO model. And that as well makes a lot of sense, because the model knows, or basically is much more precise on what features to activate. So it's the CPO model is activating fewer number of features with a much succinct or precise value of activation as well. And that is how it is, like before this, Agni mentioned that that is how it is denoising the features and giving much better output. So here, if you see the feature shifts, this is basically how we calculated like which features were activated like in CPO and not in base model, and then we calculated the activation differences. And the features, the green features were basically the correct features, like which were activated significantly in the CPO model and not in the base model, and the red ones are the suppressed or the erroneous features, which were activated significantly in the base model, but not in the CPO model. And those were the erroneous features. So if you see the increased activity, like the features with increased activity were around 892, and the suppressed features were 27,780. So which makes a lot of sense with from the previous slide as well. That's why basically it had much lesser number of L0 norm value and L1 norm for the CPO model. And the mean change is basically 0.0014. It's very less. And the number of features with no change is 0. So basically what we did, like the feature shift and all those things were basically to understand which are the correct features we need to activate in the base model to steer them to steer the base model towards the correct answer. So what we did was we uh, tried to steer the features of the base model. So we calculated a data set of 500, around 500 rows, which were the answers from the GSM, the questions from the GSM 8K datasets, in which the base model gave absolutely wrong answers to. So on those 500 rows of data set, the accuracy of the base model was absolutely 0. It gave wrong answers to those, and the CPO model gave the right answers to those. So we created a data set like that, and what we tried to do was we tried to steer the features of the base model by taking help from the activations of the CPO model, and towards, so that the base model gives the correct answer, so that it learns that which were the correct features from the CPO model, and it activates its own weights towards those. And like in the latent space, it steers the activations of its own weights towards the one that were the correct ones for the CPO model. So what we did was we attached a hook with from layer 24, which captures the activations from the downward projection layer of the base model, and then it stops and like intervenes, the hook intervenes the activations from the base model, and then it passes it to the encoder of the SAE. So the SAE then projects it into the latent space with a much higher dimension, like with sparse, like it captures, like it disentangles the features and projects into much higher space. And then with ReLU activation, and then like it steers the features towards the correct like the toward the correct direction, and then it sends it to the decoder, which then after a SILU activation, like it sends back to the base model, and then the base model provides the output. So what we saw was like a great result actually, which we didn't expect also, to be honest, but it showed significant improvement. Like with the data set, like because the base model gave absolutely wrong, like all wrong answers to this data set, like when for the 400 or 500 rows that we captured, like to do on those questions, the base model gave wrong answers and the CPO model gave right answers. But now after the feature steering, the accuracy of the base model increased to 73%. So in 73% of the questions, the base model was able to give correct answers after the feature was steered towards the CPO activations. So that showed a significant improvement. So, and then to conclude, like we found out that CPO does strengthen the reasoning after fine tuning, and the mid to late layers, like from 18 to 24, showed the most consistent gains. And after that, like after capturing the activations from the CPO layers, like the middle layers, SAE helps a lot to uncover the sparsity signature and like the disentangle the complex density activations, and like it helps understand the features in a much better way, so that we can steer the weights of the weights or activations of the base model towards that. And the activation steering provides casual evidence that the performance boosted to a significant amount from 0% accuracy on those 500 questions to a 73% accuracy. So which was a really amazing change. So yeah, that is basically it. So thank you, and please let us know if you have any questions. Thank you.
Thank you.